this video, I'd like to look at one last aspect concerning teaching model number 6, the interpretation of the information of an IR spectra, and specifically part 6, symmetrical versus asymmetrical stretches. Before we get to part 6, let's return to the table in teaching model number 7, which indicates the important signals in an IR spectrum. You can see that I'm showing the representation of the structures and the corresponding signals for the single bonds concerning the OH in an alcohol, a carboxylic acid, and an amine. We've already seen the information concerning the alcohol and the carboxylic acid. Let's now turn our attention to the amine, and what is also true is this pertains to the amide. You'll notice that the wave number for the amine and the corresponding amide is in the same region as that of the alcohol and the OH group in the carboxylic acid. So it'll be important to know how to distinguish an amine signal from the OH signal of these other functional groups. So now let's turn our attention to part 6. In part 6, I show an example of a primary amine, so this is hexane 1-amine, and an example of a secondary amine, which is the ring structure of piperidine. Now, when we look at the IR spectra, and specifically that region above 3000, when we see the primary amine, what's characteristic is that there will be a peak, but notice that the peak is not quite as dramatic, not quite as broad, not quite as deep as a peak for an OH group. Another thing you'll notice is that for a primary amine, you'll see what I sometimes refer to as bunny ears. In other words, you'll see two peaks. At first, a student may think this is because there are two hydrogens in a primary amine, but that's actually not the case. So let us draw that part of an amine that will help us see what's going on here. So here's our primary amine, and I'm going to draw it out actually two more times. Primary amine and the primary amine. So for a symmetrical stretch, we can imagine that it's an extension of the nitrogen-hydrogen bond, but in the same direction, that is towards the right, if you will, for both of the bonds. So it's kind of like the nitrogen is doing bench press or doing a push-up, in the sense that those bonds get extended, but both in that same direction, in this case towards the right. Alternatively, there could be an extension of the nitrogen-hydrogen bond, a stretch that way, but then a contraction of this other bond. Or alternatively, there can be a stretch of this nitrogen-hydrogen bond and a contraction of that one. So that would be an asymmetrical stretch. The symmetrical stretch gives rise to one of the peaks for that primary amine, and the asymmetrical stretch gives rise to the other peak. Which is which, I'm not sure, but what you need to be able to do is recognize that when you see these bunny ears, this corresponds to a primary amine. Again, it's not because there are two hydrogens, but because there are two possible kinds of stretches. For the piperidine, which relates to having a secondary amine, there'll be a single peak. Again, notice that this peak is not quite as broad, it's not quite as deep as a typical peak for an oxygen, hydrogen, and an alcohol, and definitely not the same kind of peak as the OH group in a carboxylic acid. And this is characteristic of a secondary amine. And again, there's only going to be, let me just write out our secondary amine, there's only going to be a single kind of stretch. And so there isn't a concern about a symmetrical versus an asymmetrical stretch. It's just going to be that stretching of the nitrogen-hydrogen bond towards the right.